Welcome everyone to session 2A on binary analysis. Our first presenter here is Anshunkang Zhou from Hong Kong University of Science and Technology, and he's going to talk about the system Plankton, which can reconcile binary code and debug information. Take it away.
Okay. Hello, everyone. I'm Anshunkang Zhou, and today I would like to present Plankton, reconciling binary code and debug information. So static code analysis is a popular technique used for detecting vulnerabilities in software without running them. And many mature tools have been developed for detecting many common vulnerabilities such as user free, non-pointer dereference, and memory leak, etc. So conventional static analysis has to interfere with the building process to obtain the analyzable code. However, compilation interference is not always feasible due to the complexity of the building system. And this difficulty could severely hinder the deployment of static analysis tools, which we refer to as the last mile problem. We can bypass this problem by obtaining code for analysis through binary lifting on the application binaries, which is non-intrusive to the building process and is unlikely to fail in real-world cases. So the remaining problem is, can we achieve similar static analysis results on lifted code as the compiled source code? So static analysis requires considerable source level information to work properly. And the existing tools mainly rely on two program entities to develop their algorithm, the variable boundaries and the type information. So although these two kinds of information is easy to obtain from the source code, the compiler usually discards them in the final binary code, and recovering them from the plain binary is still an undetectable problem, which could affect the precision of static analysis. So for example, the two variables at line 10 and 14 do not have any data dependencies because every local variable is associated with a distinct memory block. However, the compiler places the two variables into the same stack memory in the binary code since they have no overlapping scopes, which could result in a bogus dependence relation between the line 11 and line 15. So fortunately, we found that in a scenario like static analysis, debug information is often available, and such additional information makes reliable binary lifting possible. However, the debug information only provides a subset of source level information since the compilers cannot backward map all binary code to the source, which is the main challenge we want to solve in this paper. So let me use previous example to illustrate the challenges. So here I also show the corresponding assembly code of the source code. So the first challenge we want to solve is that the debug information usually contains incomplete variable bundles. So for example, the memory reference at line 9 is mapped to the SA variable by the debug information. However, the memory reference at line does not have any mappings. And the second challenge is that the debug information usually has incomplete type information. So for example, the R15 register at line 3 has a pointer structure type. However, the IS register at line 4 does not have any explicit types. So our key insight to solve these challenges is that various relations between code fragments allows us to complete the insufficient debug information with additional analysis. And based on this insight, we developed two new algorithms to solve these two challenges. And our first algorithm is used to complete the variable boundaries information. And the key idea here is to compute the ranges of variables by aggregating scope invariants and data dependencies between memory references. So for the previous example, the memory reference at line 9 is mapped to the SA variable. And intuitively, if we can compute these sleeve ranges, then all other memory reference can also be mapped to local variables. So for this example, we can observe that for the memory reference at line 4 and 12, there is clearly a diffuse relation between them, which implies that these two memory reference actually belongs to the same variable whose scope is at least from line 4 to line 12. And additionally, we have two more facts. The first one is an invariant that the scope of two variables should not overlap if they occupy the same memory. And the second fact is that the memory reference at line 9 is the SA variable whose size is 40. And combining those three facts, we can know that the memory reference at line 4 and 12 must be a field of the SA variable instead of an independent one. So more specifically, our algorithm extracts facts from three kinds of sources. First, we use lightweight static analysis to obtain data dependence between instructions. Second, we define the 6 scope invariants. And third, we also extract facts from the debug information. And our algorithm will aggregating all those facts and solve them uniformly to obtain the complete variable boundaries. So our second algorithm is to complete the type information. So the key idea is to transform the IRs to conform with the typing rules and eliminate incorrect type conversions. So I will take two assembly instructions from the previous example to illustrate. And here I also show the translated IR code of them. And from the debug information, we know that the R15 register has a pointer structure type. However, the IX register does not have any explicit types, which is by default an integer in x64. So we observe that high-level languages like LLVM is usually strongly typed, meaning that all operations on related values must stick to typing rules. And therefore, improper typed values must be explicitly converted to satisfy those rules, which results in a large number of type conversions in the translated IRs. So our idea here is that if we can eliminate such type conversions while still keeping the validity of the IRs, then all the operations can be assigned with proper types. So more specifically, our algorithm first leverages code optimizations to remove redundant operations in the code and make relations between values more explicit. And second, it leverages a set of Pico transformation rules defined by us to eliminate type conversion and assign correct value types. And our algorithm also iterates between these two kinds of transformations to find a fixed point that can minimize the type conversions inside the IR code. So at last, I will highlight some experimental results. So in the evaluation, we will adopt two state-of-the-art LLVM-based static analysis tools, Pinpoint and SVF. So both of them follow the conventional static analysis workflow. Specifically, they use the WLVM tool to generate the LLVM IRs for bug detection. And in evaluation, we will use Plankton to obtain the IRs from the final binary code and compare their bug detection results. So in the evaluation, we use both the Julia test suite and 17 open source projects as a bug detection target. And in our evaluation, the ground truth is defined as the bugs found in the compiled IRs. And all other metrics are defined by the result in the sections. So here I show the precision results of the two adopt static analysis tools. And the Plankton here is our tool. So firstly, we can see that Plankton lifted IRs can produce similar static analysis results compared with the compiled IRs. And on average, the false positive rate is about 17%. And we attribute most of the false cases to the fact that existing static analysis tools still cannot guarantee consistent result for two semantically equivalent but syntactically different IRs. So to illustrate, we show another group of data. So here, both WLVM and OptWLVM use IRs compared from the source code to check for bugs. And the only difference is that the later one, additionally, we optimize all errors with O3 level optimizations. And we can see that it still produces about 20% differences. So, and here are more results of Plankton's ablations. So, for example, the no stack denotes the Plankton without the variable boundaries analysis, and no peak denotes the Plankton without p-hole transformations. And we can see that all components contribute to the performance of Plankton. So in summary, Plankton can produce very precise errors for rigorous static analysis. And secondly, we also show some results to illustrate the time and memory complexity of Plankton ordered by code size. The figure shows the fitting curve and their coefficients of denomination are square 2. And the closer this value is to 1, the better the fitting curve is. And from this figure, we can conclude that the Plankton's time and memory cost goes almost linearly with the code size. And thus, it has very good scalability. So that's all for my talk. Please visit our website for more information. Thank you.
Does anyone have any questions? Please come up to the mic. No question, then if I could ask a question. So does your system depend on any version of type of compiler? Or is it generated to, like, can I use GCC and Clang and whatever to compile the binaries?
It's not dependent on the compiler you used to compile the source code. We can lift any binaries. Yeah. Thank you.
The next speaker is Fabian Parzefall. He's a 6th-year PhD student from University of California, Irvine, and his research interests are in binary analysis and recompilation. Today, he is going to present his paper, "What you trace is what you get: Dynamic stack layout recovery for binary recompilation."
Thank you for the introduction. Yeah, hi, I'm Fabian Parzefall, and as she just said, I will present what you trace is what you get, which is our dynamic approach to recover stack layers for binary recompilation. This is joint work with my colleagues Chingmay, Deshpande, Felicitas, Hetzelt, and Michael Franz at UC Irvine. So people are using all these legacy binaries that were compiled with very old compilers. And over the past 2 decades, these compilers have significantly evolved, including their surrounding ecosystems, by both academic and industry users alike. Modern compilers support architectures and hardware features and have better optimizations than the decade-old counterparts. They also provide sanitizers and security mitigations against whole classes of vulnerabilities out of the box. Usually, to modernize programs and make use of these advancements, one just needs to take the source code of their programs and compile them with the modern compiler. However, that is not always possible. Often the source code for legacy programs is no longer available, and all we have are the binaries that are essentially stuck in time. One promising approach to solve this problem is lifting legacy binaries to a compiler-level intermediate representation. If the lifter can reliably lift input binaries to such an IR without changing their base semantics, they can then be transformed and recompiled into new binaries with modern compilers. This process is known as binary recompilation. Recompilers usually target LLVM for its well-defined intermediate representation and the extensive ecosystem surrounding it. This should allow us to reuse existing tools to modernize, harden, and sanitize our old programs without having to develop specialized tools that do the same things, but have to target binaries directly. One of the key challenges when lifting binaries is accurate recovery of stack variables. In LLVM, for example, local variables are explicitly allocated within their respective function. However, before binaries are distributed, any information that directly describes program internals is removed. This includes information about local variables. For this reason, the lifter has to recover this information by itself. On a high level, this boils down to 2 questions. First, what is the set of variables in each function? And second, to which variable does the computed pointer belong to? So this information about what variables are in a binary is still present in stripped binaries, although it is not very explicit. The insight is that the program itself can reveal contiguous intervals that are part of the same variable through the way it accesses stack memory. So let's take a look at a small example for that. Here on the left side, there's a function with an integer array x of size 20. So I included the declaration of that array in this example, but this detail would not be encoded in the distributed binary. And on the right side, we have an illustration of what we know about the stack at any program point. So first, the function computes a pointer to our array and then writes this pointer to some global variable. And then later it calls another function. And here it passes the value of the global variable as argument. So if we assume that this is a 32-bit x86 program, this copies the previously computed pointer back onto the stack. And then the function bar computes some seemingly arbitrary integer, which is then used to offset the pointer that we have passed as an argument to this function. In this execution path, we know that this pointer refers to the array allocated within the stack frame of foo. And the value of n tells us how large this array is. So now all we need to do is figure out possible values for n. And so if we can figure out that the value of n ranges from -10 to 10, while the first argument of bar corresponds to the pointer initially computed in foo, we successfully identified the array. And so, as you can see, we need very, very precise data flow and value set information to actually extract the stack layout for this function. And the problem is that even source level analysis that generate this information at this granularity often do not scale to even moderately sized programs. And you can not really do this with heuristics either, because the tiniest inaccuracies will make the lifted programs fall unpredictably. This has been a limiting factor for existing recompilers because there simply hasn't been a way to recover this information with enough accuracy. And so how do recompilers have been dealing with stack memory in the first place? And the answer is they just don't recover any variables. Instead, they have developed a technique that is called stack emulation. And what this means is that rather than trying to recognize variables on the stack, all accesses to the stack are simply replicated in the lifted program. To understand this, take a look at the example program at the right. This is a simple recursive Fibonacci function with a handful of local variables. Assume that we compiled this without optimization, so local variables are just allocated directly on the stack. And when this function is lifted, its arguments are replaced with a pointer to a heap allocated area that corresponds to what is known as the emulated stack. All direct loads and stores through the stack pointer in the input binary are simply delegated to this heap object. And whenever the stack pointer in the input binary is adjusted by some offset to allocate a free stack memory, the lifted binary performs the same modification to the emulated stack pointer here named ESP. Lifting stack accesses like this means that the recompiler does not have to bother with recovery of stack variables, which is great since it vastly improves the reliability of recompilers. But it also means that for the compiler, stack variables that should be distinct objects are just part of one large opaque byte array. And when there are any load or store instructions that access the stack indirectly, most times the compiler cannot infer any meaningful properties about objects in the stack. This makes it virtually impossible to effectively re-optimize and modernize our target programs. And so this brings us to our contribution. Our insight is that by doing the analysis that we outlined earlier at runtime, we can easily resolve complex data flow and observe offsets to pointers that are only known during execution. In our implementation, we first lift the binaries to LVMR without recovering variables using the stack emulation approach outlined earlier. Since this program can already be recompiled and run, we can then instrument it similar to how sanitizers in LLVM work to analyze the stack frames of all functions. This analysis lets us directly collect stack layers incrementally across different executions of the same binary. And finally, we use these results to refine the previously lifted programs with variables. Now, this last step seems simple. After all, we have already produced a layer of each stack frame, but it deserves some more attention. So when a function computes a pointer derived from the stack pointer, what variable do we associate it with? And intuitively, we would associate it with the spilled variable x in this example, since it points right to where x is allocated. And usually that is correct. However, it could also belong to the array located further down in the frame. This might be undefined behavior in C or C++, but the CPU obviously does not care about variable bounds. And so a compiler is free to emit code that computes pointers relative to the location of an object, but are far outside its bounds. GCC in particular tends to generate code like this for loops that iterate over an array in larger chunks. Behind the QR code, I linked a little code example that demonstrates this. The reason we are pointing this out is that in our experience, most static binary analysis tools like Ghidra or IDA cannot associate these pointers with the correct variable. And naturally, if the lifter gets this wrong, the recompiled binaries won't work. But when you track pointers at runtime, the compare instruction immediately reveals the correct association for these pointers. So by instrumenting these instructions accordingly, we can record that the pointer x, so that the pointer that seemingly points to x actually belongs to the array. And that lets us symbolize these references correctly. Now, let's get to our evaluation. We used the spec in 2006 benchmark suite to verify that our approach is capable of handling real-world programs. We use different compilers and optimization flags to give us a wide variety of inputs. Our prototype recovers variables in all these programs fully automated while retaining their functionality. We compared with SecondWrite since it is the only other binary recompiler with support for stack variable symbolization. However, we noticed that it cannot recompile programs produced with current compilers. To their defense, it has been over a decade since SecondWrite was published, and some incompatibility is expected. So we also compiled the progress with GCC 4.4, which was released before SecondWrite. Here, SecondWrite works better, but it's not completely reliable either. To understand whether the variable recovery helps the compiler to reason about and transform the lifted programs, we measured the performance of the recompiled binaries relative to the inputs. When targeting GCC 12 and Clang 16 binaries, we reduce overhead from 27% without variable symbolization to 8% with variable symbolization on average. Focusing on the rightmost column, we can see that symbolization of legacy binary turns a 5% slowdown into a 22% speedup. In contrast to that, SecondWrite is unable to achieve such a speedup. The analysis has to be so conservative that it often cannot recover individual variables at all. And this confirms that precise recovery of stack variables is necessary for modernization of legacy binaries. We also measured the accuracy of our approach by comparing with the ground truth stack layouts as allocated by the Clang 16 backend. About 94% of identified variables have correct bounds, and we recover about 88% of all variables and functions that were executed at least once during tracing. For the variables that were not recovered perfectly, we also checked whether they are overlapping by some other variable we recovered. We found that about 2% of all variables are merged into some larger object, 2% are objects we recovered only partially, and about 8% are never accessed during tracing. We believe that many of the missing variables could be recovered simply by fuzzing the binary to generate inputs that drive up coverage. To summarize, we introduced the first binary recompiler that symbolizes stack variables in lifted binaries with high precision while also preserving the program's functionality. We have shown that this precision is the key for effective re-optimization and modernization of legacy binaries. In fact, our approach is so reliable that it can symbolize and modernize real-world legacy binaries completely automated without requiring any manual intervention. Thank you.
Do you have any question? We have time for.
Yes.
I'm not from the university. Because why was using C like software down?
I think it's a combination of optimizations of like often moving like a loop that executes at least once, right? Like instead of having like the loop at the condition check at the start of the loop, including the branch, having it at the end of the loop. And I think this transformation tends to shift like certain bounds around, like the way how it just adjusts like the iteration across the object. It's just a combination of various optimizations that just happen to generate this code. I don't think it is intentional to have these out of bound pointers, but they're real and they happen in all the time. Well, so they're not, you're not directly reading from them. So what you do, they're out of bounds and they're only used for comparison to terminate the execution, right? But you need to still make sure that the pointer you compute at this point in the binary relates to like is at the same position and relative to the object that you iterate over if you use it as termination condition.
It's not.
No, it's not directly. It's not used for directly to directly dereference. Yes.
So dynamic execution has this coverage problem.
Yes.
So have you looked into using symbolic execution or something along those lines to overcome that limitation?
So we have not directly looked into it as part of this work. We have looked into it as part of previous work. But we found always that the symbolic execution in particular has this problem that it cannot find like very deep paths. And so what we hope to do is like to combine like some static analysis together with our dynamic analysis, especially now that it's so much easier to perform any kind of analysis now that you've already like recovered spills and have to turn the program back to SSA form.
Thank you. Thanks, speaker. Our next speaker is Soumyakant from Stony University. He's a final year PhD student and his research interests are in the area of binary analysis, instrumentation, and its applications. And he's also on the job market for academic postdocs and industry positions.
Thank you for the introduction. Hello everyone, I'm Soumyakant and today I'll be presenting our work on binary disassembly. So the paper is titled Accurate Disassembly of Complex Binaries Without Use of Compiler Metadata. So disassembly refers to the process of lifting a binary into high-level assembly code. It has several applications like malware analysis, security hardening, binary debloating, post-compilation optimization, as well as binary instrumentation. So the primary challenge in binary disassembly is that stripped binaries usually do not have symbols. This makes it hard to differentiate between code and data. So for example, OBJDump is known to have low precision for binaries with embedded data. So past works in order to identify code have relied on pattern matching. But this essentially misses the last fraction of code. Then we have superset disassembly, which intends to disassemble every byte with the purpose of identifying every possible code, but this usually does not solve the code versus data problem, and it also leads to the increase in size of the binary code, which adds to memory overhead in certain use cases like binary instrumentation. Then we have probabilistic disassembly that uses statistical analysis on top of superset disassembly to reduce false positives. It achieves around 8 times reduction in false positive, but false positive is still high, and it is around 7%. So our approach relies on 2 categories of properties. One category is statistical properties of data to flag code, and another category is valid properties of code to flag data. So statistical properties are basically patterns that are less likely to be found in data. Lower the probability, higher the confidence of a code snippet of being code. And valid code properties are specifically the properties that must be obeyed by a program in order to ensure no crash and interoperability. Okay. So first we'll discuss about valid code properties. So these are a set of properties that are that is basically enforced using static analysis. So the first property is we check for the use of uninitialized registers. Note that this can usually occur due to programming errors, but our static analysis do not flag all such errors as disassembly problem. So we conservatively only check for issues where it will cause definite crash. For example, when a static when uninitialized register is being used as a pointer for memory difference. So the static analysis is based on abstract interpretation. The abstract domain has 2 values, top and undef. Top means basically all possible values, and undef means undefined. And our analysis is conservative in the sense we only flag an error only if a particular register is undefined across all possible values. The second property that we check for is conformance with system API. So API specifies several rules that a program must obey in order to ensure interoperability. For example, it specifies what registers that needs to be used to pass arguments between functions. So the particular property that we check for is that a function must preserve a set of polysub registers along with the stack pointer. So to evaluate the effectiveness of our valid code properties, we use 2 types of data sets. One data set is borrowed from Pang et al., which basically consists of real-world binaries and spec. Then another set of specialized data set is borrowed from Stoke Files. This consists of custom compiled binaries that have read-only data inlined within code. We use this data set to test the effectiveness of our disassembly against data embedded within code. So this chart shows the effectiveness of our valid code properties. So the left-hand side chart is the base result that is obtained if we only check for valid instructions and valid control flow. And the rightmost bar shows the reduction in false positive when you use all our valid code properties. So we can see that the valid code properties are able to reduce false positives. At the same time, they're able to keep the false negatives at low. This is particularly because our properties are conservative in nature, and we only check for critical violations. So, although we have reduced false positive to some extent, we are still left with over 1% false positive. And to reduce it further, we rely on statistical properties of data. So like I said before, these are evidences of code that are rarely found in data. And it is helpful in prioritizing true code over non-code or data. So these properties have been used by previous works, but one key difference is that they consider the distribution of byte values in the data region as uniform. Whereas we made an observation is that the data is not really uniformly distributed, rather it is skewed. In particular, 30% of the byte values are zeros in the data region. So when we use this non-uniform data distribution to compute the probability of, say, control flow transfer instructions, we observe a difference in orders of magnitude between the non-uniform distribution computed value and the uniform distribution. So this table shows the probability computed for all types of control flow instructions. Also, we experimentally computed the frequency of control flow transfers in the data region and compared it with the computed values. And we can see that the non-uniform distribution based values are much more closer to the experimental value than the uniform distribution. So this experiment shows the strength of statistical properties. So here what we do is we basically set a threshold and say that if code snippet has a score below that particular threshold, then we reject it as data. Now we can see that at higher threshold values, the false positive comes close to zero, but false negative has gone very high. So now we have two sets of properties. How do we combine them? If we do a conjunction, then we'll have a high false negative because we'll inherit the false negative of our statistical properties. And if we do a disjunction, then we'll have high false positive. So we came up with a prioritized error correction algorithm. So this algorithm takes all function entry points as inputs, and it calculates the statistical score for each of the pointers. Now, if a pointer has a score that is greater than a given threshold, then we accept it as a valid score, valid code, or else we pass the pointer through valid code property checks. If a pointer conflicts with another valid pointer, then we basically discard the conflicting pointer. So in the previous slide, we saw how we use statistical properties to prioritize our code. Now this slide shows how we use valid code properties to further rectify the control flow graph. So the input to our valid code analysis is the function entry point and the CFG, and the output is whether the function is true or not. So there are several aspects of validating the control flow graph of a function. One aspect is non-returning calls. So some calls might not return, and the compiler, knowing that the call will not return, might put non-code or data right after the call. So we must identify all such calls and flag the fall through as non-code. So for this, we pass the call's fall through address as the input to the analysis. And if the analysis says that the fall through is a true function, then the call is non-returning. Also, if the fall through is definite data, that is, we find some invalid instruction or control flow in the fall through, then also the call is non-returning. The next aspect of a function's control flow graph is function entry point. So to validate each of the entry points, we again pass the function pointer as the input and check its output. And another aspect is jump table targets. So these are basically switch case blocks in C++ code. So to validate these targets, we check each target individually. So in this case, the input is function entry point as well as a jump table target. Now, since the jump table target is a part of the control flow graph, so our valid code properties must hold true when the jump table target is also made a part of the control flow graph. Okay, so this slide compares the effectiveness of our error correction techniques against other disassemblers. We use the same data sets as before. So the leftmost chart is for the data set that has inline data. We can see that our disassembler DASA has around 3 to 4 times better false positive and false negative in compared to any other disassemblers. And when it comes to real world binaries, our disassembler is able to produce near zero false positive and false negative error rate. So to summarize, we introduced 2 sets of properties to improve disassembly accuracy. So static analysis based valid code behavior identifies data, and the probabilistic data properties helps us in prioritizing good code and resolving conflicts. So combining these 2 properties, we achieve 3 to 4 times better accuracy than existing disassemblers. Thank you. I'll take questions. Okay. So the input to our analysis are indirectly released codes that are basically can be called from anywhere from the world. So we assume that such code must obey the ABI since that is to ensure interoperability. Yeah, so that is our assumption that we operate under. So in case certain functions do not follow ABI, they will be reported as false negatives. Yeah.
Any other questions? Regarding the data properties that we are using to classify something as data, are they specific? Did you find them to be specific to an application or a class of applications, or is the probability distribution, do you expect it to be the same for all binaries everywhere?
Yeah, we expect it to be the same for all binaries. This is because, so we first took the test, you can call it as a training set. And we observed the distribution, then we tested it with a much larger test set, and the results come out to be true. So we assume that this will hold true for all the binaries.
All the desktop server applications.
Yes, yes, yes.
Thank you. Thanks, Peter. What do you think? I have picked up this session is from Chinese Academy of Sciences. And it's going to present his work on tips inferring intermediate pain sources for effective vulnerability analysis of IoT device firmware.
Okay. Hello, everyone. My name is Zhou Liu. I'm from University of Chinese Academy of Science. This talk is about vulnerability and size of Internet of Things devices firmware. I propose the concept of intermediate source and design methodology to infer it. Before introduce the specific method, I briefly introduce the relevant background. With the development of IoT technology, embedded devices have become an indispensable role in modern life. Large-scale deployment and the lack of real-time updates make IoT devices popular targets for cyber attacks, such as StarNext and Mirror. These cyber attacks can not only lead to privacy leaks, denial of service, and unauthorized control, but may even threaten the device itself, the environment, and the life by manipulating the device. Firmware is the core of embedded device operation and is stored in Flash. Various components are packaged in firmware to implement the operation of the device, such as bootloader, kernel, and application. In applications, vulnerabilities in executable binaries are a major factor in device cyber attacks. The reasons are as follows. First, executable binaries are usually responsible for communication, data processing, and execution of various devices. These applications are the main development targets of manufacturer. Therefore, vulnerabilities are likely to exist in released devices application. Moreover, vulnerabilities in the executable binaries have the potential to be exploited remotely. The vulnerabilities discovered are commonly found in devices of the same model and series. Timely discover vulnerabilities and reporting them to manufacturer is an effective way to improve device security. Static taint analysis is suitable for firmware vulnerability analysis because static taint analysis doesn't need to rely on the specific execution environment of the firmware. Moreover, static taint analysis can achieve high code test coverage. However, performing efficient taint analysis on firmware is not an easy task. Firmware unpacking and binary reverse engineering have developed well, allowing us to analyze binaries in firmware. Therefore, existing work labels interface library functions that receive external untrusted data as taint sources. The received data is marked with a taint label and tracked to check for vulnerabilities. However, effective taint analysis relies on the establishment of the complete data dependencies in the binary. To achieve accurate analysis of data dependencies, existing work relies on the assistance of heavyweight program analysis algorithms such as symbolic execution. Combined with the complex data processing of the binary, this method leads to path explosion and memory explosion. Expensive overhead prevents the firmware from being fully analyzed, resulting in false negatives. Of course, all approximation analysis methods inevitably introduce many false positives. To improve the effectiveness of taint analysis rather than relying on heavyweight techniques, we take a different and fresh perspective. We hope to shorten the length of the data flow path from the taint source to the sink, which can significantly reduce the complexity of the analysis. Therefore, we need to find new starting paths for taint analysis, which exist in customer functions. For example, function 16 in the figure can be used as a taint source because such functions always exist after classical taint source. To process data, we call them intermediate taint sources. Determining whether a function in striped firmware can be classified as an intermediate taint source is not trivial. First, intermediate taint sources do not have a definitive detection criteria as classical taint sources and have various implementations, especially across firmware of different device vendors. Second, finding intermediate taint sources requires reverse engineering, not only function to model the semantics, but also other functions to understand the inter-procedure data and control dependencies. Third, firmware is usually stripped of debugging information and symbol tables, resulting in loss of semantic information, such as function names and variable names. Finally, it is often not possible to apply dynamic analysis to find the intermediate taint sources, because vendor protections for device make it difficult to obtain runtime information. The concept of intermediate taint sources is inspired by our observation that the logic of handling a user input in internet-connected IoT devices. First, the user input data received is structured and usually contains multiple fields. Then, if the user input data meets the format requirements, the data is saved to memory. Finally, if the user input data needs to be processed, one or more fields are fetched from memory for subsequent processing. It is worth noting that retrieving the user input data from memory often involves the implementation of a customer function. This function retrieves data based on the index and returns it for use. by other functions. Therefore, it can be used as an intermediate source. This design makes the intermediate source behave like memory manipulation functions. Considering there are various standard library functions that operate memory, such as the string copy, memory compare, and string. We treat the implementation of this function as anchors and analyze the similarities between anchor functions and customer functions to identify intermediate sources. Our methodology mainly consists of 3 stages. First, we pre-process the firmware, including unpacking, determining binary programs, reverse engineering. Then we extract the behavior feature representation of the function through program static analysis. Finally, we react the customer functions by performing behavior similarity analysis on the customer functions and anchor functions. The first stage unpacks the firmware to obtain the file system and selects the binaries containing the network interface as targets for analysis, because network communication is a major source of cyber threats to IoT devices. Then we find all libraries on which the selected binaries depend. At the same time, we identify library functions with memory operation behavior and the anchor functions by function names. Finally, the selected binaries and dependencies libraries are converted to intermediate representation to facilitate data analysis. The second stage is to extract function behavior feature. To infer intermediate tint sources, we design a function representation called behavior feature vector. The behavior feature vector includes 2 types of features. Structure features represent the static properties of a function, such as the number of basic blocks and the existence of loops. Flow features represent the dynamic properties of functions, such as whether function parameters, control loops, or branches. To extract these features, we leverage the under-constrained symbolic execution technique to generate control flow graph and call graph for each function. So we perform graph analysis on the control flow graph and call graph of the function to extract structure features. For flow features, we divide them into intra-procedural and inter-procedural extraction. Firstly, we apply rechain definition data flow analysis to the control flow graph of a function to understand how the parameters of the function affect its branches or loops. If there is a dependency relationship between variables and parameters, the corresponding feature value is true. For interprocedural flow features, we analyze the function calls and backtracking through the memory structure to find the origins of the arguments. If the date can be represented by a constant, we treat it as an address. Then, if the address is in the read-only section, it is treated as a string. The third stage scores the behavioral similarity between customer functions and anchor functions to infer intermediate sources. However, scoring customer functions directly may lead to false positives due to the order of the magnitude differences. To this end, we first perform cluster analysis on all customer functions and screen candidate customer functions by statistic characteristics of classes. Finally, the anchor functions are used to perform cosine similarity calculation to infer the intermediate sources. We implemented the prototype phase. We evaluate phase on 59 real firmware samples. After getting the ranking results of phase, we need to verify whether a customer function can be used as an intermediate source. The intermediate source function should extract and return a part of the user input. As shown in the table on the left, at least one of the top 3 results can be used as intermediate source with an average of 89%, which proves the effectiveness of FINS. Advanced work Brainstorm cannot find any tate source in firmware samples. The table on the right shows some addresses of the intermediate sources. We applied phase to two tint analysis engine Coyote and STA to demonstrate how intermediate sources help improve the vulnerability discovery capability. Coyote performs tint analysis based on the symbolic execution technology. After adding intermediate tint source, Coyote discovered 15 more bugs. STA is a static tint analysis engine based on IDA Disassembly results. Intermediate sources helped STA find 339 more bugs. In latest firmware samples, 67 bugs have been confirmed, and 21 of them have been awarded CVE IDs. Then we conduct experiments on behavior feature vector to illustrate its effectiveness compared with variants of BFV and advanced work, augmented CFG and attributed CFG. BFV achieves higher precision. To illustrate the necessity of behavior cluster stage in intermediate source inferences, we use the anchor functions to directly score customer function, and the precision drops to less than 10%. We propose a concept of intermediate tint sources to tackle the challenges of performing effective tint analysis on striped IoT device firmware. Then we propose the methodology phase to automatically discover intermediate tint sources from striped firmware. In the evaluation of the 59 firmware samples, phase infers intermediate source with a top 3 precision of 89%. Moreover, intermediate sources improve the performance of the tint engine in finding vulnerabilities. Thank you.
Did you measure the false positive rate or the false negative rate of the system?
Yeah.
What was the?
It's about so in static tint analysis in firmware, it always exists false positive. And when we use intermediate sources to aid the tint analysis, false positives decreased compared with advanced work. It's about 20%. 20%. Yeah.
Thank you.
Okay, thank you.
Thanks for the
Like that.